In this video, let's look at some more level curves. So we're going to calculate the level curves of this three-dimensional graph, z equals e to the negative x squared minus 2y squared. And this notation here is telling us basically the x and y values. So it's saying x is between negative 2 and 2, and y is between negative 2 and 2. So it's specifying really just to look in this little square region here, but we probably look at some other regions as well as we work through this. So remember, the idea of a level curve is we're looking at the projection of, let's look at this here, the projection of the intersection of a plane with the three-dimensional surface. So we've got a plane that's parallel to the xy plane at some elevation, and that plane will cut through your surface and intersect in some one-dimensional arc, some one-dimensional shape. And we're going to project that shape onto the xy plane, and we're going to graph those, and these are called level curves. They give us the curve at different levels. Now in this picture, these level curves are all the same shape, and that certainly can happen. They don't have to all be the same shape, but it is fairly common with a lot of surfaces. So the idea is we want to think of z as a constant. Okay, so let's go here and look at our equation. So we want to look at this and we want to think about z being a constant, and we want to graph this. Now, you can just keep it as z if you want, but a lot of times people will put some other variable in there to represent their elevation. Let's say we put in c. I'm going to think of z as some constant, okay? So we have c equals e to the negative x squared minus 2y squared. All right, so I want to change the form of this to get a better graph. So what I'm going to do is I'm going to take the natural log of both sides to get all those variables out of the exponent. So let's see what we have. We have the natural log of some constant, which is the elevation that we're concerned about. And then the right-hand side simplifies to negative x squared minus 2y squared. All right, so I'm going to go ahead and multiply both sides by negative 1 just to get rid of those negatives on the right-hand side. Now this is starting to look like something I might recognize. I have an x squared and a y squared. So now I'm thinking circle, ellipse, some kind of conic section. I'm going to simplify this a little bit more. I'm going to take this negative and I'm going to bring it up here to the exponent. That's a property of logs. So I get natural log of c to the negative 1, or 1 over c. And let me write that out in a couple steps. So if I bring that negative up, it becomes negative 1. And then I can write that as 1 over c. So this is not going to be the easiest thing to graph, but I might use Desmos to help me graph this, but this is definitely an ellipse. And if I wanted to put it in perfect ellipse form here, I would do something like this. This is going to look a little bit funny here, but I'm going to write this 2 as over 1/2. Right? That's the same as 2, right? 1 divided by 1/2. And so if you were thinking of it in terms of an ellipse, this would be the square root of this would be your values on the x-axis and your vertices on the x-axis, and the square root of that would be your vertices on this axis, and then you would get your ellipse. Okay, but let's go ahead and use Desmos to take a look at this for certain values of c. And let's start to think about what values of c we can even use, right? Because we got a natural log in there. Maybe we should go off to the side and think about that for a second. All right, so natural log of 1 over c. What kind of values can I put in there and get an output? Let's say this is just equal to y or something like that. So remember, the graph of the natural log is going to look something like this, and it has an x-intercept of 1. This is a rough sketch here, but it comes like this. It intersects at the point 1, 0 and continues like that. So let's just say this is natural log x equals y. So the domain is x has to be greater, not equal to, x has to be greater than 0. It's never equal to 0. All right, so over here then, I would say, well, then my 1 minus c has to be greater than 0. which would happen if c was positive. As long as c is positive, 1 over c is going to be greater than 0. Okay, that's great. But now we have some more stuff going on. We have this equation. Let's look at the equation in this form right here. Let's go back to this other sheet. And we want to think about, when does this have a solution? We could try values. X squared plus 2y squared. Right, okay. So let's just say I let c equal 5. Remember, that's an elevation, right? Let's say I have an elevation of 5. So if I do the natural log of 1/5, here's my natural log. So natural log of 1 over 5. Okay, here we go. 1 over 5 is 0.2 natural log. I get a negative. So I would get about negative 1.6 equals x squared plus 2y squared. All right, let's think about this for a second. And we could go try to graph this if you want, but x squared is a positive value. X squared is a positive value no matter what. Y squared is a positive value, and if I times that by 2, that's going to be positive. So if I add those together, I'm going to get a positive. So no matter what values of x and y I pick, this is never going to be equal to negative 1.6. So if I put, what that's telling me then is that there is no intersection at an elevation of 5. Right? If I have an xyz situation and I have 5 and I have some plane at a height of 5, that plane is not touching my three-dimensional surface at all. My three-dimensional surface is either all below it or all above it. Okay, not every elevation is going to have an intersection. So we really need to figure out what values of c will produce an output here, and those would be the elevations that will produce an intersection. So what do we need in that case? Well, we need the natural log of 1 over c to be positive, because this whole thing right here is greater than or equal to 0. If x and y are 0, then we could get 0. So the natural log of 1 over c has to be greater than or equal to 0. So let's take a look at that and see what we get. When does that happen? Well, let's change this back to c to the negative 1. All right, then we can bring this negative 1 back down in front again. And we could divide both sides by negative 1. Now, when we divide by a negative, what happens? Right, we have to flip the sign. So I need the natural log of c to be less than 0. I need the natural log of c to be less than 0. Well, let's look at this graph over here. Let's say this is the natural log of c equals y. This is my c-axis, and this is my y-axis. When is the output less than 0? Less than or equal to 0, right? It's right here. That's when it's less than or equal to 0. So in order for that to happen, I would need c to be between 1 and greater than 0. We can't have c be 0 because then we'd be dividing by 0, right? I can't put a 0 in there. All right, that was a lot of work just to figure out that for this problem, when we're thinking about level curves, we only have level curves when c is between or including 1, between 0 and 1, including 1. So that's the only elevation that our surface goes between, is between 0 and 1. So it's all above the xy plane. I want to think about my surface here. I could have z equals 1. My surface is definitely above the xy plane, but it's below, or maybe just touching the plane z equals 1. So it's all in between here, and including this plane, okay? So when we pick our level curves, we need to pick c between 0 and 1. So now we certainly could crank some of those out, which is a lot of work, but we could do some kind of a little c and then 1 equals x squared over natural log 1 over c plus y squared 1/2 natural log 1 over c, or you could put the 2 back up in the top and do some kind of a table, and let c equal 0.1, c equal 0.2, c equal 0.3, like that. That's pretty tedious, isn't it? That's just screaming for Desmos. So let's go take a look at Desmos. All right, let's put in 1 equals x squared over the natural log of 1 over c. Hopefully it'll ask me for a slider here in a second. Hopefully. Then what do we have? Plus, oh, let's just put the 2 back in the numerator. 2y squared, there's my slider option, over natural log 1 over c. Okay, so for my slider now, I've done the work to know between -10 and 10 is not going to work. As a matter of fact, see, look, there's no graph. Let's see, are we going to see? Oh, there's a little graph right in there. Now I'm getting a graph. Okay, when am I getting a graph? Well, I'm getting a graph when c is between 0 and 1. Not including 0, but that's okay. Okay, so if c is 0, I don't have a graph. Let's slow this down a little bit and think about what's happening. Let's just go one direction. One direction. Okay, so when at an elevation of 0, I have nothing. So it's not intersecting. That would be right on the xy plane. And as the elevation gets higher, what's happening to my level curve? It's an ellipse. It's getting smaller and smaller and smaller. Can you picture what this graph is going to look like? And we could graph a whole bunch of level curves in here. We just have to copy and paste this thing and see how far apart they are, right? To see how close the level curves are to each other. We could put our step in as 0.1 so it doesn't go smooth. It kind of jumps, and that could give us an idea about how close they are. So they're getting pretty close as it gets close to 1. So I'm thinking it gets pretty steep there. Whereas at 0 to 0.1, they're a little bit spread out. Now it feels like they're getting closer and closer and closer and closer together in the same increment of 0.1. So I'm thinking it's pretty steep as we get close to the XY input of 0, 0. All right, let's go take a look at this graph. You ready? Drum roll, please. There you go. So here's the graph, z equals e to the negative x squared minus 2y squared. So what's happening is it's, we have this mountain sort of like what we expected, but it continues forever. It's not like a half a hemisphere or anything. It comes down and it just gets closer and closer and closer to the xy plane, but never touches it. And that's really a characteristic of this e to a power, right? If you think about just the graph of e to a power, it has this characteristic of approaching. Usually we would look at the x-axis, but never touching it. But here it's approaching the xy plane and never touching it. There's actually like space between the graph and the xy plane. So if you wanted to graph all of the level curves, then what you would want to do is go back over to Desmos and put in values of c, and then just copy paste this business. It seems like you should be able to copy paste this. Maybe I'll use my keyboard shortcuts. Yeah, there we go. Take that out and take out your slider, and you could just put in 0.1, and then the next one put in 0.2. So I'm using my keyboard shortcuts because it won't let me highlight it. So, Control C, Control V for copy paste, and then put these in. I won't do the whole thing, but then you could go all the way up to 0.8 or 0.9, okay, and you could see your level curves.